Hi everybody, welcome to another video in Business Calculus, section 11.6, Optimization. In this section, we will have a lot of application problems of finding absolute maximum and absolute minimum. Right, let's look at the first example. A developer wants to build a rectangular range next to a river. If he has 6,000 feet of fencing and he does not need to fence the side adjacent to the river. So have the river. Assume the river bank is straight. We find a rectangular fence, rectangular range next to the river, like that. And we have 6,000 feet of fencing. We do not need to fence the adjacent to the river. What is the largest area that can be enclosed? Correct. Now, if it is rectangle, if this x, this is x, and this will be y. We want to find the largest area, meaning that we need to find the area. In this case, is x times y, length times width. So we need to maximize that. So the problem is maximize area. Now there's a problem with this. Of course, we only use calculus, but up to this point, we only have calculus of one variable. So everything have to be written in one variable only. So either in terms of x or in terms of y. It's not that bad because we do have 6,000 feet of fencing, meaning x plus y plus x is equal to 6,000. X plus y plus x equal to 6,000, meaning 2x plus y is equal to 6,000. So y is equal to 6,000 minus 2x. And we can substitute this into y. So that equal to x. Y is 6,000 minus 2x. So that gives us 6,000x minus 2x squared. Right, so function one variable is good. Now, we have a theorem on previous section saying that if the function is continuous on the closed interval, then we guarantee to have a maximum or minimum. So if we have that closed interval, then we guarantee to have a solution. So that's good. We need that. Now, think about this. We have 6,000 feet of fencing, right? So we have to say it. But regardless of whatever that is, we're talking about x and y, which is the measure of the length and the width. X and y cannot be negative. So let's start with that. The measurement cannot be negative, right? So I have to be greater than or equal to 0. So I have x greater than or equal to 0, which is good. Now what is y? So why don't we substitute that into here as well? So not only we want x to be greater than or equal to 0, we also want 6,000 minus 2x also greater than or equal to 0 as well, right? Because that is y. So we subtract 6,000 on both sides and then divide by -2. However, when we divide by a negative number, we have to reverse inequality. Divide by a negative number on both sides, reverse inequality. So that gives us x less than or equal to 3,000. So we have x greater than or equal to 0 and x less than or equal to 3,000. So we have x is between 3,000 and then 0, 0, 3000. Right. So when we put that together, the problem becomes, we said, the problem becomes maximize the function 6000x minus 2x squared for x between 0 and 3000. So we can say, just write like that, from 0 to 3000. So we translate a work problem into that math problem. Now the rest is easy. That's what we've been doing. First, find Greek or vowels. Greek or vowels on the interval of 0 to 3000. Notice that we don't need to worry about the boundary. We're going to test the boundary with the table anyway. So just open interval. Right, take derivative. 6000 minus 4x equal to 0 does not exist. Derivative equal to 0, 6000 minus 4x equal to 0, or 4x equal to 6000. So x equal to 1500. Of course, the unit is feet. Does not exist. The derivative is defined everywhere, so we do not have anything. So bottom line is we have only 1500 for x, one Greek point in this. Now it is the one Greek vowels. If we only have one Greek vowels, we can use the first derivative test, second derivative test. Both of those tests we find local maximum or local minimum, but with that also absolute max and absolute mean. What I do is the easiest one. I just put everything back into the table. Original function. A, the area is 6000x minus 2x squared. We have 0 and 3000 on boundary, and the Greek vowels inside 1500. If we have a closed interval like this in the problem, the best is just put in the table. Right, now if we have 0 down to x and 6000x minus 2x squared, right? If we have 1500 down to x, and we do that, right, that is 4,500,000. And then if we have 3000 down to x, evaluate that, we have 0. So clearly this is the maximum value, maximum area, sorry. So maximum area is equal to this when x equal to 1500 and y is equal to that. So we find y at x equal to 1500, y equal to 6000 minus 2 times 1500. 6000 minus 3000 is 3000. The conclusion is max area equal to 4.5 million. The unit will be square feet. Happen when x equal to 3000. I'm sorry, x equal to 1500 and y equal to 3000 feet. Right. So Again, we're trying to find a function, and if we find the condition that we need, if it is a closed interval, even better. And after that, we just have the absolute maximum and absolute minimum problem. I will find all the critical values and then determine. If there's only one critical value, that will be easy. Most likely that's going to be the values. But we still need to confirm that it's actually the maximum or the minimum, even though we find the only values here. So that most likely that is our answer. But we still need to show that it's actually the maximum. Right. So the optimization problem is usually just like that. We convert a work problem into a math problem. A math problem, we have two parts: the function to be optimized and the domain. The function and then the domain. And once we have that, we just find the absolute maximum and absolute minimum for the problem. Right. Here is a similar problem. A homeowner has $20 to spend on building a fence around a rectangular garden. 3 of those sides will require a wire fencing, $2 a foot. The other one, good fencing, $6 per foot. Find the dimension of the area with the largest garden of $220 worth. So it's still rectangular, right? So you have one side that require the wooden fence, and the other two sides it's just wire. So this rectangle, so we have x and x, then y and y. What we maximize the area of the largest garden. So the area once again is equal to x times y, and that is the function to be maximized. So the problem is maximize the function x times y. Now 3 sides of those are from wire, makeup wire fence, $2 each, and then the other side wooden fence, $6 a foot. So the total $320. Of course, we're trying to head up to $320. So let's see. X here, that the wire fence, so that $2 each foot. Y here, also wire, $2 each. This X, $2 each, and this Y, wooden fence, $6 each, and we want to use $320. We use all of them, right? To simplify this, we have 4x plus AY equal to 320. Right, why don't we divide everything by 4? We have x plus 2y equal to 320. Of course, we can solve for either x or y. In this case, why don't we just solve for x? Just subtract the 2y on the other side. Of course, I do need to divide by 4 on both sides, right? So, x to y, 80. Right. So we can substitute that to here. So if a equal to x times a20 minus 2, substitute to x, right? Sorry. A equal to 80 minus 2y times y. Sorry about that. Multiply them out. 80y minus 2y squared. Right, so we have the function to be maximized. Now we need to check the condition. Once again, we need x and y greater than or equal to 0. We have the function for y, so it's good. Just keep it as y, but we will substitute into this x. (80 minus 2y greater than or equal to 0). Solve for y. 2y greater than or equal to negative 80. Divide by negative 2. Once again, divide by negative number. Reverse inequality. Less than or equal to 40. So we have y greater than or equal to 0, less than or equal to 40. Right, so we put that domain of the problem with the function to be optimized. So we said the problem become maximize the function on the interval from 0 to 40. Right. Of course, the rest is simple. Find critical point. Critical values on the interval. It doesn't have to be close here because we're going to check with the boundary later, and it depends on what we have here first. Alright, derivative 80 minus 4y equal to 0 does not exist. 80 minus 4y equal to 0. Subtract 80, negative 4y equal to negative 80. Divide by negative 4, so y equal to 20. Does not exist. We have none. Right, so y equal to 20. Certainly 20 is in this interval. So that's good. Like I said, since we have the boundary, it's much better. Just put everything in the table. With the original function, we can determine which one is the max, which one is the mean. The function is y, right? We do have the boundary of 0 and 40. Critical values in the middle, 20. Right, evaluate this function. 0 is turned to x. 80. I just use x instead of y, so that because the x I just hit that button, y I have to hit alpha 1. Right, so for x equal to 0, we have 0. And x equal to 20. Evaluate that function. 800. So the area, maximum area is 800 feet. Square feet, sorry. And now we have 40 is turned to x. Now we have 0. Obviously, this is the maximum. So we say the absolute maximum, or the maximum area is 800 square feet. So maximum area is equal to 800. That when x equal to 20. By the way, 800 for area, that's square feet. And for the length, that's just feet. Right, we have x equal, sorry, keep doing that, y equal to 20, and we can just substitute back in here to find x. Put 20 in here, 80 minus 2 times 20, 80 minus 40 is 40, x equal to 40 is fit. Bottom line is we have to find the function of one variable to be maximized or minimized, and ideally we want the domain. Even better if the domain is closed. We just use a table for that. Right, so that is optimization, finding the maximum. And look at the problem when we find the minimum. Look at the same idea of the problem. I suppose that owner, the same owner that we talk about, say that 800 square feet, which what we have on the previous problem, is not enough. He wants 1250 square feet. Now what would be the minimum cost? Enclose the area, given that the dimension of the garden. I mean, the cost of the fencing is still the same. So we still have the same scenario. We have x, and y, Right, in this case, different though. What we want is to minimize the cost. And the cost is based on $2 for each foot on this side, plus $2 for each feet on this side, and $2 for each foot on this side, and $6 for each foot on that side. So this is the function for x plus ay. This is the cost function to be minimized. So slightly different. What we have in this problem is we do want to have exactly 1250 feet square feet. That is the area. We want the area to be that. The area is x times y, by the way. This time it is a constant of 1250. So function of two variables. It would be nice if we only have one. So in that case, we have to solve for either x or y. Let's solve for y. So we will have the function of x. So that gives x and x cancel. So y equal to 1250 divided by x. Right. Now that's good. We can just substitute. Into here. So c equal to 4x plus 8 times 1250 divided by x. That the function need to be minimized. Right. Is there any condition? Well, we know that x and y, a measurement, cannot be negative. But if we put 1250 divided by x greater than or equal to 0, we just need x to be positive. Because if x positive divided by positive, it's going to be positive and greater than 0. So in this case, we only have the lower bound from 0. X could be extremely long, right? Because we minimize the cost. The x could be extremely long. In that case, the cost will be huge, right? X could be 10,000 feet, a million feet. It doesn't matter. The area, as long as is 1250, is fine. However, the cost will be expensive too. So, bottom line, if we want the area, it could be a square, or it could be extremely thin, or even extremely thin. the area of that very thin rectangle probably could be the same as that. So in that case, the only boundary we have is greater than 0, from 0 to infinity. It cannot be 0 though, because we cannot divide by 0. So in this problem, 8 times that, by the way, that would be 10,000. So the problem becomes minimize the cost function of 4x plus 10,000 x for 0 to infinity. X just need to be positive. If x equal to 0, that will be undefined. Right. Now the rest is easy. Find critical values in here and then go from there. Critical values. Could be more than one on the interval. Right, now take derivative. And we'll rewrite this as 4x plus 10,000 x to negative 1. Derivative of that is 4. Take negative 1 down, 10,000 x to negative 2. Over x squared multiply x squared top and bottom, so we have 4x squared minus 10,000 on the top. Right, so equal to 0 does not exist. Remember, every time we have rational function, I prefer to combine to one big fraction. So we say the top is 0, the bottom is 0. Right, derivative equal to 0. That means the top is equal to 0. And derivative does not exist. That means the bottom is 0. Right, divide by 4 on both sides. X squared equal to 2500. Right. And then take the square root on both sides. Don't forget there's plus or minus. So plus or minus 50. The bottom is x squared equal to 0, so x equal to 0. By the way, on the interval here, the 0 doesn't count, the negative 50 doesn't count, so the x equal to 50 is the only critical values. Now that is important, right? Because this one, we have an open interval. So unlike the previous problem, if the interval is closed, just go ahead and evaluate the boundary. That's easy. This one, we don't have the boundary to evaluate. So with hope that we only have one critical values, and we do have that. Rule number 2. On the interval, there is only one critical values. X equal to 50. Now, if this is the only critical values, we need to show that this is the local minimum. We're trying to find the minimum values, absolute minimum values. So if we can show that it is local minimum at x equal to 50, that is also absolute minimum, right? Because when we have one critical values, the local is also the absolute, right? So to confirm that it is the absolute max, or this is the local, I'm sorry, to confirm that it is the local max or local mean, we just need to use the second derivative test, because the derivative is very easy to evaluate. So I use the second derivative test. Second derivative equal to, take down the negative 2 to 20,000 x to the negative 3. And if we put 50 in here, divided by x cubed. Second derivative, when we put 50 in here, so 20,000 divided by 50 cubed. So that is 0.16, which is positive. Second derivative is positive. That means it's concave down. That's why we need the face, right? Second derivative is positive, so it's concave up, and therefore the minimum at 50. So we say local mean, therefore absolute mean occurred x equal to 50. Now if x equal to 50, y is equal to that. I give us 25. So x is equal, y equal to 25 feet, and x equal 50 feet. Right? And we have x, we have y, we have the cost function. So the minimum cost for x plus ay 4 times 50 for x plus a times 25 for y. That's 200. So the cost is $400. Right. So unlike the previous problem, this problem we don't have the boundary. It is not on a closed interval. So in that case, we hope to have only one critical values. If we have two critical values, we still need to put on the table like this. But then we have to use the limit, because the boundary is not there. We have to use the limit. Luckily, we don't have to, because this one an open interval, but we only have one critical values. So the local mean is also absolute mean at x equal to 50. And then we can find y. Then we can find the cost, $400. Right now, let's go to other application. Maximizing revenue or profit. An outfit supply company sells X permanent markers per year at P dollars per marker, and the price demand is given by this. What should be the company charge for the markers to maximize the revenue? What would be the maximum revenue? Right. So in general, revenue is the income is equal to the quantity that we sell times the price for each. So the quantity times the price. And if we let X be the permanent markers, so X is the quantity, and P is the price. So we have that equation. We can substitute. Okay, the quantity is going to be X. The price is going to be P. Substitute that in here. We have X times 10 minus 0.001x. So that is the revenue. Let's say that is the function of X. Multiply them out. 10x minus 0.001 x squared. Right, from this one, x is the quantity, cannot be negative. So that's all we have. Or we can say we want to maximize the revenue for x being positive. So the problem is maximize the revenue function 10x minus 0.001 x squared, let's say on the interval 0 to infinity. Actually, we might have it equal to. In that case, we not produce anything. In that case, the revenue would be 0. So clearly, that's not going to be 0, right? Because if x equal to 0, we're not selling anything, and the revenue would be 0. That should be the case. Right, so that is the problem. So similar to what we've been doing, find the critical values. On the interval. By the way, we're not going to take 0 because when x equal to 0, we have no revenue. So that's obviously not the maximum that we're trying to find, right? So that's common sense there. Right, we take derivative. Give us 10 minus 0.002 x equal to 0, does not exist. Right. So take derivative of this equal to 0. And then we can solve for x plus 10 on both sides, or subtract 10 on both sides. And divide by that. $5,000 markers. And there's not exist. That always defined, so there's none. Right. Now, like I said, x is not going to be equal to 0, so we just completely throw x away. I mean, completely throw 0 away. Only consider from 0 to infinity open interval. And so in that case, we only have one critical values, and then we can use the same method that we used earlier. Right. So number 2, on the open interval 0 to infinity. By the way, x not only it cannot be 0, it cannot be 0.5, so it have to be 1, 2, 3, 4, 5, only natural numbers. But we only have one critical values. Only one critical values. At x equal to 5,000. So there's a lot of different way to do that. First derivative test, second derivative test, or we don't want to put everything on the table but have to use the limits. I've used a second derivative test because the derivative is easy to determine. Second derivative will be negative 0.002. So it doesn't matter what x is, the second derivative is negative, meaning it concave down. So that means this point is a max. So local and therefore absolute, because it is only one critical values. So the absolute max or local max at x equal to 5,000. If we want to find the maximum revenue, put 5,000 back into the function. If we store that into x, and the revenue is minus 0.001 x squared, and that's 25,000. So the revenue is 25,000 when we sell 5,000 markers. And if we put 5,000 here into the price demand function, we're $5. So we sell each marker $5, and then we sell 5,000 of them. That's the revenue of 25,000. So the local and absolute max will be at 5,000 markers, and the revenue at 5,000 we did calculate earlier, that 25,000, right? So yeah, so here we evaluate the revenue function, and that gives us $25,000, right? So that's the maximum revenue when we produce 5,000. Now, suppose the cost of X permanent markers is given by this. What is the company maximum profit? Now, I'm just going to write out the function and just write out the problem. The rest will be very easy. Will be just like this. So I just want to write in this problem, the profit is equal to the revenue, the income, minus the cost. Revenue we have earlier, the cost is just given here. Revenue is this 10x minus 0.001 x squared. That revenue, the cost is 5,000 plus 2x. By simplifying this, we have 10x minus 0.001 x squared minus 5,000 minus 2x. Right, simplify this, 10x minus 2x is ax. So the problem is maximize the profit. Ten x minus 2x, that plus ax minus 5,000. So maximize that. And of course the same condition, x should be positive to infinity. Of course, if we not produce anything, if x equal to 0, once again, we have no revenue, and therefore the profit will not be maximum when we not produce anything. Right. Of course, the rest of the problem will be similar to what we've been doing. So I'll let you do that. Right. Anyway, so we have application problem, and pretty much all the application problem, we translate the work problem into a math problem. We have two parts. What we're trying to maximize or minimize, and interval. If it is a closed interval, just put on the table with the original function. If it's not closed interval, we hope that we only have one critical value. So in that case, the local is also the absolute. If we don't have the closed interval and we have more than one point, then we still have to put, if there's more than one critical value, put on the table. But we have to use the limit because the boundary is not closed in that case. Right. But that's all I want to cover for this section. Thank you for watching, and see you in another video in business calculus.